let's go over the solutions to the logarithmic functions part 2 exercises. So let's solve the following logarithmic equations by putting them in exponential form. So here we have log of 7 minus 3x equals 2. So let's write this in our exponential form and then solve it. So remember, the base of the logarithm is going to be the base of the exponential expression. Logarithms are equal to an exponent, and then what you're taking the logarithm of is the result of taking that base to this exponent. So remember, the base of the common log is 10. So that'll be 10 raised to this exponent of 2 will equal this result 7 minus 3x. So 10 squared is 100. We'll subtract 7 from both sides and divide both sides by 3 to get x equals negative 31. Here we have the natural log of x plus 12 equals 2. The base of the logarithm, base of the natural log is e, so we'll have e raised to this exponent will give me this result, or that e squared equals x plus 12. We'll subtract 12 from both sides, and we get that e squared minus 12 is the exact answer. Now, if you want, you can put this in your calculator. You can take e squared and subtract 12 to get a decimal approximation of about negative 4.61. All right, let's do our change of base formula. So if we wanted to change log base 3 of x into a base 7, remember it's going to be log new base of what you were taking the logarithm of divided by log new base of the original base. So to change log base 3 of x into log base 7, it will be log base 7 of what we were taking the logarithm of, which was x, divided by the log base 7 of the original base 3. Take log base 5.5 of 10 and turn it into common logarithms. Remember, common logarithms is base 10 and it's just written as log. So just like before, it'll be the log of what we were taking the logarithm of, which is 10, divided by the log of the original base 5.5. But remember, the base of the common log is 10, so this is log base 10 of 10. Well, 10 to what power is 10? That's 1. So log of 10 is 1, so that can be simplified. And if you want to do a decimal approximation, you can put into your calculator 1 divided by the log of 5.5, and you'll get about 1.351. Take log base 17.2 of 921 and turn it into natural logarithms. It'll be the logarithm of the natural log of what we were taking the logarithm of, divided by the natural log of the original base. And we get log base 17.2 of 921 is the natural log of 921 divided by the natural log of 17.2. Or about 2.399 if you put that into your calculator. All right, given that log base b of 2 is about 0.5234 and that log base b of 3 is about 0.9861, let's approximate the following. So let's do log base b of 16 over 27. So we're going to have to put this in terms of log base b of 2 and log base b of 3. Using our properties of logarithms, we're taking the logarithm of two things being divided. I can break that up into the logarithm of the numerator minus the logarithm of the denominator. Now, let's turn 16 and 27 in terms of 2's and 3's. 16 is 2 to the 4th. 27 is 3 to the 3rd. Now, what you're taking the logarithm of is being raised to a power. You can bring that power out front. And once you have log base b of 2 by itself, just like this, you can do that substitution. Keep in mind, the 2 is being raised to the 4th, not the entire logarithm, so I cannot do my substitution here. I have to wait until I bring that 4 out front. And the same thing here. Now I can plug in those decimal approximations for each of those to get that log base b of 16 over 27 is about negative 0.8647. Let's do another one. Log base b of 6b. What we're taking the logarithm of, we're taking the logarithm of two things being multiplied. I can break that up into two logarithms being added, log base b of 6 plus log base b of b. So again, we know our log base b of 2 and our log base b of 3. Well, what is 6? 6 is 2 times 3. So I can break this up even further of two logarithms being multiplied, or a logarithm of two things being multiplied into the log of the first plus the log of the second. And now we have a decimal approximation for this. We have a decimal approximation for this. But what about this? Log base b of b? Well, since these match, we do know that b raised to the 1 power is b, so the exponent that this logarithm is equal to is 1. And when we add that all together, we get that the log base b of 6b, this should be 6b, is about 2.5095. Let's find the exact value of the log base 6 of the fifth root of 6. Well, first of all, let's start by getting rid of that fifth root and writing it as 6 to the 1/5. Now, we do have a property that does tell us, our elementary property number 3 tells us if the base of the logarithm and the base of the exponential function match, they cancel each other, and we would be left with this 1/5. But a lot of us forget that, so another thing we can do, what we're taking the logarithm of is being raised to a power, we can bring that power out front. And now, what 6 to what power is 6? We know that this logarithm here is 1, and that gives us that same answer of 1/5 if you had remembered elementary property number 3. Similar here, find the exact value of the natural log of the cube root of e to the 5th. Again, we'll write that in radical as a rational exponent or a fraction exponent, which will be 5/3. Elementary property number 3, if you remember that, you know this is automatically going to be 5/3, but if not, what we're taking the logarithm of is being raised to a power. We can bring that power out front. And the natural log of e is 1, and we end up with 5/3. Now let's use the properties of logarithms to expand into as many logarithms as possible. To do this, we need to ask ourselves, are we taking the logarithm of two things being multiplied? Are we taking the logarithm of two things being divided? Is what we're taking the logarithm of all being raised to a power? And if you answered yes to any of those questions, then you need to use that property of logarithms to expand. And you keep on asking those questions after each expansion until you answer no to all three questions for all of your logarithms. But a question will arise. What if you answer yes to more than one of those properties? Which one do you start with? And the answer is, it depends. So what you need to do is make sure whichever property you are starting with, it should be very clear where all the pieces go. For example, here, if we were going to start with log base 4 of x times y over z, we are taking the logarithm of two things being multiplied, x times y, and two things being divided. This is all over z. So we have at least those two properties. Now, if you try to start with the multiplication property and you do log base 4 of x plus log base 4 of y, where does the z go? It should always be very obvious to you where each of the pieces go, otherwise you may be trying to start with the wrong property. So here we'll start with the division property, because we clearly have a numerator and we clearly have a denominator, and that logarithm will be the log base 4 of the numerator minus the log base 4 of the denominator. And now we can separate this using that multiplication rule to get that this is log base 4 of x plus log base 4 of y minus log base 4 of z. Now notice I'm not taking the logarithm of two things being multiplied, divided, or all being raised to a power, so this one is done. The natural log of x to the 5th times x minus 4 to the 3rd, all over 2x plus 7. Well, we do have some exponents to worry about. We have things being multiplied and we have things being divided. There's no big exponent. It's not all being raised to a power, so I'm not going to start with that third property. And just like above, if I start with the multiplication property, where does the 2x plus 7 go? So we're going to start with that second property and take the natural log of the numerator minus the natural log of the denominator. Now I can break this up. These logarithm of these two things being multiplied will be these two logarithms being added. Here, what I'm taking the logarithm of is being raised to a power. Here, what I'm taking the logarithm of is being raised to a power, so I can bring that power out front. And now I am not taking the logarithm of two things being multiplied, divided, or all to a power, so that's how I know that I'm done. Log base 2 of 5x to the 4th over the square root of x, all to the 3rd power. Here, it's all being raised to a power, so I can bring that power out front. And I'm going to change the square root of x to the 1/2. Now I have the logarithm of two things being divided. I can break that up into log base 2 of the numerator minus log base 2 of the denominator. Now, this one big logarithm here is equal to these two logarithms being subtracted. Since I want 3 times this one big logarithm, then I need 3 times both of these logarithms being subtracted, which is why we distribute the 3. Now, here you might want to bring out the 4, but the problem is only the x is being raised to the 4, not the whole thing. But we do have an operation between 5 and x to the 4th, and that's multiplication. So we can break that up into the log base 2 of the first plus log base 2 of the second. And now the 5 is separate. Now what I'm taking the logarithm of is being raised to a power. I can bring that power out front, and the same thing here. So we have 2 log base 2 of 5 plus 12 log base 2 of x minus 3/2 log base 2 of x. So you might think that we're done, but take a look here. These are like terms. For logarithms, like terms have the same bases with the same insides. So here I have 12 log base 2 of x. Here I'm taking away 3/2 log base 2 of x. I can put those together to get 21/2 log base 2 of x. The natural log of x to the 5th times the square root of x to the 4th times z to the 7 all over w. Let's start by getting rid of this square root and writing it as a fraction exponent. Now, one of the things we've talked about before, if you don't have addition or subtraction inside the parentheses, you can distribute the exponent. So I can distribute the 1/2 to the 4 and the 1/2 to the 7. And notice that 4 over 2 will reduce. And so now I have the logarithm of two things being divided. I can take the logarithm of the numerator minus the logarithm of the denominator. And here I have the logarithm of 3 things being multiplied, so I can break this up into 3 logarithms being added. Now I have exponents. What I'm taking the logarithm of is all being raised to a power. I can bring that power out front. I am no longer taking the logarithm of 2 things being multiplied, added, or divided, or all to a power, so that one is done. And that's it for these exercise solutions. I'll see you next time.